Hi, I'm Keegan with the Econ Tutoring Center, and I'm here to talk about understanding derivatives as opposed to focusing on the computation. So what you need to know beforehand is just all the algebra concepts that are normally expected before you take a calc class. A derivative in math, in general, is defined as the slope of the tangent line at a particular point along a curve. So let's talk about what that means. Suppose you have this function, we could call it y equals f of x, and either y-axis or x-axis. And suppose this, of course, is our function graphed. Then at every point along this curve, you could describe a line that's tangent to it at that point, and that means it kind of just barely touches it, and it runs parallel kind of at that point. So the slope of this line is what you find when you take the derivative of something. For example, we could also look at, say, this point, and that would give us the slope of the line right here. And all that is like a really precise way of saying it, but in loose terms, you could think of the derivative as being the slope of the function itself at a particular point. And so that's really helpful because it tells you how much a thing is growing at a particular, how much the function is growing or shrinking at a particular point. And so because of that, you can talk about what the effect of, say, x is on y at a particular point. So suppose we talked about the function y equals x squared, right? And that looks like this, right? At approximately 1, it grows at about 1. At x equals 1, the slope is 1, so it's growing kind of at a unit rate. And then it starts to rapidly accelerate the further along the curve you go. And you can find exactly what the rate of growth is in terms of x by taking the derivative. Basically, you can think of derivatives as being a ratio that expresses the change in a function or in one variable that results from the change in another variable. When we take the derivative, we write dy over dx. We also write sometimes f prime of x. But this is really helpful because it tells you that this is a ratio of what's the change in y for a change in x. The main concept that you should remember is that it's all about how one variable changes in response to a change in a second variable. So let's do an actual example. Suppose our function is pay, which is equal to 10 times the number of hours. Suppose it's an hourly employee, and they get $10 an hour. Then how much money they make is this P is equal to 10 times H, which is the hours, right? So we could say that P is a function of H, and it's equal to, of course, that. dP over dH is equal to 10. And what that means is that the slope is always 10. And basically every hour that you add is going to give $10. So every additional hour that you work is going to give $10. So that's the effect of hours on pay. Now suppose we have an alternative project that we can take as opposed to our hourly job, and this project pays equal to h to the 3 halves and we might even say minus 20, then this is a project that is going to give us increasing returns the more hours we spend on it. And it's also got this initial setup cost. And so we might ask, how many hours do we have to work before this starts paying as well as the hourly alternative, which was P, so this is 10H, right? So at what point is this paying on an hourly basis more than this one? Well, the first step to figure that out is to take the derivative. In rough terms, that'll tell us what the hourly rate is at any number of hours worked. So in this case, once again, we're going to focus on not how we find the derivative, but what it means. So dp over dh equals 3/2 h, 3/2 the square root of h. Okay, which is of course equal to 1.5 times the square root of h. All right, so that tells us that for any number of hours, the slope of the function, which is kind of like the hourly rate, is 1.5 times the square root of how many hours we worked. So in rough terms, you could say if we've already worked for 1 hour, then h equals 1, then the derivative at 1 hour at h equals 1 is 1.5 times the square root of 1, which is of course 1. So we end up with 1.5. And so that tells us that we're making approximately $1.50 per hour. And that's a good way to think about it, just conceptually, that the effect on our pay of the number of hours, of an increase or decrease in the number of hours, is $1.50 when we're at h equals 1. In fact, it changes continuously. So for example, if h equals 1.5, then you have 1.5 times the square root of 1.5. You have 1.5 times the root of 1.5, which equals approximately 1.84. And so that means that if we're thinking about the change from 1 to 2 hours, then by the time we've gotten to 1.5 hours worked, the derivative has already changed to 1.84. And that's why you have to be a little bit careful in saying that that you're making $1.50 per hour, because once you add an hour, over the course of that hour, your rate is changing, so you're not going to make exactly $1.50 more. But once again, like it's a good rule of thumb and way to think about functions and understand them. Well, what if we put in way more hours? Say that h equals 60. Well, 1.5 times the root, so times the root of 60, 11.62. That's the marginal or that's the effect of h on pay, the effect of hours worked on pay at 60. So it's the slope is now 1162. That's kind of how pay grows in response to hours worked. So we can already see that at 60 hours, this project is already paying more than the derivative was, than this one was, which was $10 an hour. And if we actually wanted to find where the what the point is that this starts paying more on an hourly basis, we could actually set the derivatives equal to each other and solve for the h that comes out of that. Now we're going to go ahead and find the number of hours where these two alternatives give the same hourly payout. And so to do that, we take our two derivatives and we solve for the h that results, the number of hours, right? Get rid of move the 1.5 over to here. So that's what, 3/2. We have the square root of h is equal to 20 over 3. And we can go ahead and square that to get h, absolute value of h. H equals 400 over 9. And if we simplify that to some decimal number, we would find exactly the point where this project starts to pay more on an hourly basis than this one. And it's probably going to be a bit higher than 40, right? Because if we imagine this 9 to be a 10, it's going to be like, then it'd be 40, but it's a 9, so it's going to be a bit higher. One other thing that we often use derivatives for is maximization problems. So imagine that our business makes profits equal to 15q minus 5q squared, where q is equal to the quantity of items that you make and sell, right? So then here we have a function that's p is a function of q, and we can ask ourselves, well, what's the effect of changing the quantity on p? And that would give to find that effect, to identify that effect, we would normally take the derivative, and that would tell us the effect, that would tell us dp over dq, which is change in p with respect to a change in q. Then you have 15, the derivative here is 15 minus 10q. And we can go ahead and solve for this function. Is going to look like this. It's going to be a bit different, but the point is that there's going to be a maximum. Okay, so if we want to find where that maximum is, we could look for the point where the derivative is 0, because that's where the slope is 0, right? And so, and the point where the slope is 0 is kind of peaked, and after that it's going to go negative. So we could go ahead and find where this equals 0. So we just set 15 minus 10q equal to 0. And then we have 10q equals 15. And so q equals 1.5. And what that means then is that 1.5 is the maximum of this function. So you only want to make 1.5 units of our good. So hopefully that helped you to understand kind of how to work with derivatives and think about them. If you have further questions, feel free to leave a comment on the video or come into the tutoring center or ask your professor.